What we're going to do is just count everyone's opinion on that and see how it is. So it's a little bit similar to the all the way at the beginning, which is a nice kind of round off. Yeah, people on Zoom also vote. Just type your answer or whatever, and Mathieu will help us count. And we're gonna see how it goes.
I'll tally.
Yeah, Jared is tallying. I will try and count. So the first question, as you all see, mass transfer is the dominant uncertainty in all of binary evolution. I say raise your hand if you agree, and keep your hand down if you don't.
Lika, they're saying there's no audio on.
There's no audio on
Zoom can hear now, though?
Yeah, we can hear. Well, I can hear.
But do you hear this also?
Yeah, I can hear that.
Oh, okay.
I think there was no audio when we fixed it.
Okay, cool. Okay, raise your hand if mass transfer dominant uncertainty in all binary evolution.
Raise your hand if you say yes.
Yes, raise your hand if yes. Raise your hand if yes. I'm gonna count. Keep your hand up.
But are we seeing like all as in every binary or all as in the full population?
I didn't write the question.
This the question is as stated with degeneracies. Make your own.
Out of
Parse it how you will.
Yeah, I don't know.
Not in
Like, how do
every
you see it?
binary.
Not in every out of.
Like, is it in the majority of binaries? Is mass transfer the dominant uncertainty in the majority?
In the field of?
Are you most worried about out of all uncertainties? Are you most worried about mass transfer? That is going to be the question. So, raise of hands again because I lost count. Okay.
Out of all the uncertainties, are you most worried about mass transfer?
17 people. Oh, 18. I also raised my hand. How many are we in total?
I don't know.
How many are we still?
How many survivors?
We're 26 people left in total. If I didn't miscount.
Plus Zoom.
Plus on Zoom. I might have miscounted. I'm not good at counting.
There's 3 people that are on the
There's 8 people on Zoom. This is probably.
There should be 5 people on Zoom. Yeah.
Yeah, there's
many were
26
we,
people in
Monday?
person.
Sorry,
3
8
people on
people
Zoom.
minus 2 because there's 2 Zoom.
He's asking.
Also, I'm one of them, so I.
All the other uncertainties that you know of. Everything you know of. Okay. Okay, so he was. So we.
Simon asked, as opposed to everything else.
Yeah. Okay, we're getting there. We're figuring it out. Okay, that's the good majority out of the 26. Not everyone. Oh no, it's 29, I think.
29 plus
the
3.
Zoom. Yeah. It's 26. Okay. Next. Sorry? The total is 29 people. We can figure that out. Okay. Next question. We learn more from comparing to individual systems versus populations. Okay. Who votes? We learned more from individual systems. Raise your hand. And if they're going
either or.
There's probably going to be a both or.
Oh.
Okay, let's start with individual systems.
Wait, is there both or not? Because it changes how some of us vote.
Well, I would also vote for both.
That's not an opinion.
Is there anyone who would not vote for both if that was an option?
So
Okay,
if you had to choose.
If you had to choose, one of those annoying questions. You had to choose individual systems or populations. Individual systems, raise your hands.
What do I want to learn? The answer changes depending on what I'm investigating.
3, 4, 5, 6, 7, 8. Individual. Is the rest?
+1.
+1 Shashreen. You can't do Shashreen, right? Is the rest populations? Populations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, don't focus on outliers. But yes, it depends on the question.
Completeness.
And we need
I would
both.
argue focus on the outliers only.
Completeness is
No,
23
no,
out of
you're
29.
biasing yourself. Focus on the majority. Don't focus on the gravitational waves. It's not like I'm not doing that. But those are the outliers. Okay, next question.
Next question.
There's a
Yeah, there's a
yeah,
clicker.
use that.
Yeah, you can.
We are most likely to first observationally constrain A, common envelope, alpha, envelope efficiency, B, stable mass transfer efficiency, beta, or zeta, stable mass transfer stability. Okay, who votes alpha?
But we have constraints on common envelope efficiency from observations. We have constraints on stability of mass transfer, right? So
Okay, let's but define it better. Constrain it down to
5 sigma.
10%. A factor of 2.
factor of 2.
How do I vote that alpha doesn't exist?
I want to vote that too. Okay, the extra bonus question. Common envelope alpha doesn't exist. Agree, if you raise your hand if you agree.
with alpha, you still
No,
need
it's-
much
yeah, it's a number.
You still need more string numbers.
Mixing
Okay,
like alpha doesn't exist.
Okay, so
either.
I think no one votes for common envelope alpha. Let's put it like that. Who says we'll skip that? We will constrain the mass transfer efficiency within a factor of 2. And I'm gonna say for all binaries then. Before we're going to,
None of the above.
before we go, okay.
It's easy, right?
Oof, these questions are difficult, man.
Yeah, bro.
Where are we gonna make more progress first?
Okay.
Mass transfer efficiency or mass transfer stability? Rephrase it completely. Who votes mass transfer
Observational
efficiency?
progress? Or
Whatever you
theoretical
feel
progress?
like.
It says observational.
Oh,
It says
observation. Okay,
observationally.
where are you gonna make more observational progress? Mass transfer efficiency? Raise your hand if you think it's mass transfer efficiency first. 1, 2, 3.
We don't need to move maybe to
Oh.
Sorry.
20. Anyone on Zoom?
21.
21?
Shazleen,
Okay.
and no, actually, plus 2. Simon, 2 says that.
Okay, and who thinks we will first make progress on the stability? Is that the rest, or is there anyone who abstained from voting?
I do think that we will make progress on stability first, but not with from observations.
Oh,
Probably.
do you care to elaborate? Do you want to?
I would think that some instability, stellar structure and hydro, and the people that are able to do that. I'm sorry.
I was saying, I do think that stability will be constrained before mass transfer efficiency, but not from the observations. I think stability, the way to go is 3D hydro and stellar structure.
But the two things go hand in hand. If you don't have the accretion. But the two things go hand in hand. So if you don't have the accretion efficiency, then you cannot determine zeta. Right? So then you would get them simultaneously from those simulations. You have to assume one.
Yeah, but
The other.
mostly to get a stable mass transfer efficiency, you also need the donor, right? Very
Yep.
precisely.
But in order to determine the stability, you need to make an assumption for beta. Like if
Yeah,
your
but I
beta
would
changes,
believe
it
that you
could.
can get away with a range of betas to constrain your stability. No?
Oh, yeah, the two things are intertwined.
Okay.
This is discussion. This is good.
Yeah.
Yeah. You want an interactive workshop?
Okay. But so there's not many people who think well, you says we make progress on stability, but from theory, from hydro simulations. I think among you
Raise,
also
raise your
raised
hand on stability, just to get the
Was
number.
there someone else who is saying stability first? Observational. Oh, yeah. Yeah.
Observation. 1, 2, 3.
Oh, it's just no?
Yeah, like my comments about that is because people like observe some post mass transfer system, And we can, I mean, sort of, like we know the mass ratio, like for the post-mass transfer stability, like, sorry, we know the mass ratio for those post-mass transfer system, sort of can trace back, like what's the initial mass ratio before the mass transfer. And so like can like kind of tell like what initial Q can have stable mass transfer. Because like for, let's say for blue straggler, many of them are observed like in binary system, like they have a white dwarf as a companion. So like the white dwarf is the initial donor, and after some stable mass transfer, the accretor becomes blue straggler and donor becomes white dwarf. And also, yeah, observers already found like many blue straggler in those kind of binaries. So we kind of know like, yeah, and also we can take the specs, like doing UV spectroscopy on the white dwarf, so we know the mass, temperature, or like mass still like model dependent, but we can have some information for those post mass transfer system and can trace back what's the like before mass transfer, what's the information, and also say something about stability. This is my, yeah.
Oh, that's a good point. I feel like the room is reasonably optimistic, at least over the last two, which is good because we're at the workshop for stable mass transfer. So I mean, kind of nice that we're not all depressed, regardless. Okay, I'm gonna continue if this works. Yes. Okay. Uncertainties on accretion efficiency depend more on stellar evolution phases than on the mass. And on the mass ratio? No.
She says the mass.
I don't really know what they mean either.
So it's like the
Like
efficiency of mass transfer, mass dependent, like from 10 to 20 solar masses, you have.
So they mean more like the thermal time scale. If it's thermal time scale dependent, then that adds on to how much mass is being transferred, or because efficiency just means how much mass is transferred in this context, you mean, right?
Yeah, and like, is it only PQ dependent or is it also initial donor mass dependent? How does the efficiency look like as a function? Like,
yeah,
it's not only a function of PQ, but if you go to higher masses, then the PQ diagram changes.
We could say as a function of stellar evolution or as a function of PQ space.
yeah. Okay. Who thinks the accretion efficiency depends more on the stage of stellar evolution compared to the PQ diagram, or like the mass? Okay.
Stellar function also.
1, 2, 3. One. Everyone set? Oh, Preem, you keep like.
I clearly don't know what I want.
1, 2.
By evolution, do you mean like thermal and nuclear timescales?
18 people.
I was thinking main sequence or something.
Yeah, I was thinking that too, but I don't really know what they meant here.
Turns out when you do PowerPoint karaoke,
You didn't write the karaoke.
and yeah, you didn't write the song.
Dude,
so you don't
and
know how to
did
sing it.
everyone else vote for the I was one of the other? I actually don't know. I think my answer would be, I don't know. Maybe.
Yeah.
I also would switch to I don't know if that was.
Evolution sets changes time scales much more. So
Yeah.
that's why I voted evolution.
But it's all related. But yes, please say.
What I was saying is that the evolutionary phase changes the time scales of the donor star and accretor star
Yeah.
More throughout the evolution than the masses. So that's
The initial
why.
mass and period that sets what evolution that's what I'm confused about. Okay, maybe confusing question.
You're kind of
Let's oh, you already switched? Can you switch one back?
I just did switch one back.
Okay. Spins in X-ray binaries inform us about mass transfer more than spins in gravitational waves.
Oh yeah.
Oh, it's a good question. Wait, were you raising your hand for what?
Left.
Okay.
X-ray
X-ray binaries first.
Yeah.
Actually, it's just everyone minus No, it's everyone. It's everyone. Wow, yeah, we agree on something.
And yeah, 2 more from Zoom on X-ray binary as well. Doesn't break
So
the
it doesn't break
consensus.
uniformity.
Unanimous decision.
Nice.
Problem solved.
One Zoom abstention.
I don't think we're unanimous on that.
Traditional ways.
Will you go to the next? We will be able to say whether
Compact object.
objects hosting post-mass transfer systems we observe have been mass ratio reversed.
Oh, that's an
Oh.
interesting question.
Okay, so the observed systems with a more massive black hole and a less massive black hole, did the more massive black hole come from the more massive star
Or, the
or
less
not?
massive.
That is mass ratio reversal. If not, then it's mass ratio reversal. And the question is, will we be able to tell if they were mass ratio reversed or not? The first will be yes, we will be able to tell if they are mass ratio reversed.
But using gravitational waves only.
Yeah, you will be the gravitational wave sample.
This just said, but this says, will we be able to say whether
You can put
the
it.
population of compact objects is mass ratio reversed or not?
Want to say something, or are you raising
two
your hand? to
black
I'm
vote?
just gonna say
Or
double
two
white
compact
dwarf
objects.
temperatures.
Okay, so
Sorry?
I would just say double white dwarf temperatures.
Yeah,
Mhm.
yeah, okay.
Yeah.
Who raises their hand on yes, we will be able to tell? I think.
all
yes.
cases.
I feel like a lot of people here are like, I have no clue. But I'll just follow. Is there anyone, let me put it like this, is there anyone who says no, who would like to say why? Or, yeah, right now.
I'm going to take this to be in all cases, and I think that we're always going to have model designer seats for the binary black holes where you just can't tell.
Okay, yeah, that is a fair answer. You can't always say everything for all of the things that I agree with. But I'm hopeful that there will be a lot of systems where we'll be able to tell if they were mass ratio. Okay, let's continue. Ground versus space-based gravitational waves will tell us more about mass transfer. Okay, so the question is, will ground-based gravitational wave detectors tell us something about mass transfer, or will space-based gravitational waves detectors tell us something about?
Is it
mass
like which one
transfer?
will give us an answer faster, or which one?
Which one will tell us, once both of them are happening, which will tell us more?
What will be more informative? Yeah, so, but I think that is the question. That is what they're probably alluding to, is like, are we gonna learn about white dwarf mass transfer? Will that tell us more than all these black hole mergers that we'll see with ground-based detectors?
Physics may not be the same.
Huh?
The physics may not be the same.
It might not be, yeah.
The dominant mechanism may not be the same.
Again, I think like mass ratios and double white dwarfs tell us directly about mass transfer stability and accretion and all of that. And binary black holes are way tougher because you have the metallicity dependent winds and the supernova kicks and all of that.
Not to mention,
Also on top, like space-based, well, also you have the interacting systems that you see transferring mass in action. So I'm sorry, but I'm gonna clearly go for space-based.
Yeah, I think I would agree.
all right, raise your hand for ground-based will tell us more. All right, Reynold. you
Well,
got
it'll tell us a
one.
lot. I mean, like Einstein telescope and everything will still be amazing because we will see everything. Yeah. Well, it does tell you of a different spaces, as you said, like what if white dwarf progenitors don't work the same as, black hole progenitors, which they probably don't, then you just miss that whole population by only focusing on the white dwarf. So it will tell you more about massive star stable mass transfer, I would say.
But that wasn't the question.
But we're interpreting the question. So
This is powerful.
Adding a mass
it will tell us more about
like
if you
Lisa
you
is not
don't
gonna
group a
say-
IMF wave to your question, then I think a larger parameter space will be learned from. I'm sorry. I'm just, trying to join Reinhold and being a bit.
I see, you're attached to LIGO or DT.
Also, we should build
nice.
DT. That is.
Lika does not believe in stars less than 10 solar masses.
Have you ever seen one up close?
Yes, it's the only one we've seen up close.
I don't know, we're pretty far. I think it's all
relative.
fake.
Everything we do.
Oh, yeah, we're doing the same again. Infinite computational power. One of our models is going to be representative of real mass transfer physics.
Do we also have infinite computational time?
Okay.
Yeah, one of them,
Should we
but which
vote
one?
first and then give answers? So
Does this mean that one of our current models will be right, or that will be able to simulate actual mass transfer?
I think second.
Oh, then yeah, of course.
I don't know. I interpret it as the first. I'm gonna do a weird thing and just have everybody say yes or no with your own interpretation. And then I'm going to ask people to explain their interpretation and their answer. So whatever you think the question is, do you think the answer is,
Sorry.
yes? Raise your hands now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. And then who wants to elaborate on 11? 11. Who wants to elaborate on their yes answer?
So many degrees of freedom.
Plus one for yes.
Yeah, plus one.
You said, is it 12?
Plus one.
Yeah, I did 11 plus 1 to get 12.
Oh.
So the way I interpret this question is that with infinite computational power, you can make an infinitely good 3D MHD simulation. And in that case, if you do it very well, that would tell you as good as possible how actually mass transfer would work, assuming you use the right physics.
For however many systems you can assume. And then you have to analyze the data. And then.
Yeah.
Not in the question.
Yeah. Yeah, well, it's the infinite compute is nice.
Wait, but
And just for the other interpretation, I changed my interpretation to yours, which is whether, well, I don't know if it's yours, but it's whether one of the current models that we have will turn out to be the right model if we had infinite computational power to check it. And I think the answer to that, no. I think you need to do the 3D hydro simulations.
Yeah.
That was his interpretation.
Yeah. Is there, okay, assuming the rest raised their hand for no, interpreted as no, are there people who want to respond to that?
Yeah, I mean, I can also set a simulation that simulates me as Superman. Doesn't mean that with infinite computational power, it will simulate me being Superman in reality, and it will represent the reality of facts. So, I mean, yeah, I mean, we have to get to the physics right, which is a big if.
Yeah. I agree with that. I think we don't know the physics, so we don't know how to write it code.
Right.
Okay, maybe we don't know physics, but the way I interpreted this question is I just focused on representative. And I already think that without infinite computational power, we already do 3D models of a variety of things that are very representative of physics that we see in a lot of phenomenon. So maybe it's not going to be perfect, but we're going to get a good idea. And of course, having infinite computational power is just going to make it
Infinitely better?
I don't know. Do you believe in computational irreducibility?
Yes.
Okay, that was a good one.
Oh.
Did we do 2?
No, I think this is it. So you want to
The last question?
You click.
Oh,
Okay.
no, but
This
we
is the
have
last
8.
question.
Why do we have 7
Yeah, I
there?
think there might have been some loss in questions where everyone answered one on that. I might have.
We skipped.
One of
over
us might have skipped.
Which one did we skip?
Here, let's go back. Okay.
Gravitational waves versus EM.
We said
Wait, did we do that question a long way?
spins in which one?
Gravitational waves versus
We did this
We did
one.
this.
electromagnetic.
Uncertainties, stellar evolution phase, spins. Will we say compact objects? Gravitational wave, ground versus space. Gravitational. Oh, we skipped this.
Gravitational waves versus EM observations will tell us more about mass transfer. I think is going to be very biased. Who thinks we'll learn more from gravitational wave observations about stable or mass transfer in general?
It's a kind of mass range issue,
Yeah.
right? Not like,
You need both a little bit.
yeah.
But you will also need the majority of the population, which is visible in EM.
I'll say a gravitational wave signal is cleaner in some meaningful sense.
The masses are very well
Yeah.
reduced, which is very nice.
Degeneracy. Well, there's still degeneracies.
Would everyone else vote for EM? Is there anyone who wants to vote to make a controversial statement or non-controversial statement?
Be provocative.
I think the controversial statement, like what Sylvia was saying earlier about like
The point that Sylvia was making earlier about Lisa and interacting white dwarfs, that's gravitational waves, and it might teach us more, but only in that mass range. It's not going to be useful for higher masses.
Where's the second mic?
So I don't want to go like too
Sylvia just has
Kobayashi on this question, but
Reinhold,
it's like
Sylvia.
these things are inherently very complementary, right? I think we should never fall into the trap of putting them against each other because you really get different dimensions of information about the masses, for example. So
I love that unifying answer. I think it's very true. You shouldn't pick.
Maybe there's another aspect is that I think the discovery of gravitational wave signal like in 2016, like after that, like the whole binary evolution or stellar evolution community like sort of benefit from that. So we get more funding like to do research. Or, like,
that's a good way to answer.
yeah, although like I vote for EM observations, but actually like gravitational wave like thing is like like just help this whole community a lot. Yeah. Also, I think the Poseidon code like start to develop like also after like 2016, right? Yeah, so we get a big fund and can have like more than 50 people in this developer team and build the code.
It's true. Yeah. So gravitational waves, but only because it gets money that gets us EM observation.
I think the answer is just both. I would stick with Evan's answer. We shouldn't put them against each other. And Mathieu as well. Last question. How many years until we agree on whether critical rotation suppresses most accretion in stable mass transfer?
You already agreed that it doesn't.
Let's go order.
doesn't,
Order.
right?
Let's go half orders of magnitude.
Did we
One,
agree?
3, 10.
Okay, wait. We should rephrase it. We should see how many years until we know how much critical rotation or whether critical rotation
suppresses
when critical.
So
How
I'm just we'll just shout. So I'm gonna start shouting numbers. Raise your hand when you think. I'm gonna do it in half orders of magnitude. So 1, 3, 10, 30, etc. I'll start with 0. Who thinks we already do? You?
Not in our system, but there are cases that are quite obvious. There are systems that are quite difficult to explain otherwise.
Okay. What about 1 year, next year? 3 years.
You have to count also. Should I yell and you count, or should I count? Wait, we had 2 and 0. Wait, what was it?
We had
were saying doing 0, 3.
3. Well, 0, 1. No, there was no one at 1.
0, 1, 3.
3, 10, 30, 100.
Okay, and the 100 is gonna be here in the middle.
All right. Who says, yeah, so we have 0, 2. Who says 3 again? Raise your hand for 3 again. We got 1, 2, 3, 4, 5, 6, 7.
Online?
Online?
Nobody's.
I think
7.
Okay.
10. Who thinks in a decade? 9, 10.
10, 10.
10, 10.
30?
All right, who thinks 30? 1, 2.
Not the most
Who thinks 100 years? Who thinks never?
Meg.
One thinks 100.
It's a nice distribution.
That's a good distribution.
Peaks around 10.
Yeah.
Oh, wait, there were,
Oh.
Simon says 12, which was not.
That's 10. 12 is 10.
Says 10. Let's read 10.
Oh,
and-
okay, so it's 12 at 10, so 10 is peak.
We do have systems that we kind of are convinced that they are fully conservative, right? How do you do fully conservative without suppressing?
Yeah, but I guess the question is not so much, not so much, do we think that it is always or never the case? Because there, I think you're right. We can already exclude that there is always critical rotation, or there is never critical rotation reached, because both of those cases we can say no. But I interpret it as, can we know which systems will have undergone critical rotation? And I'm pretty hopeful that in the next few years, people are now looking into it. We'll see it. Did you want to say something?
The aim is probably to find the beta Röhrschlob overflow as a function of omega, right? Or omega over omega crits. So there could be that this is still true, but you get very conservative accretion where you're very short periods and tidally locked, and then you don't go to critical rotation, right? That's the.
That's.
But then you're not reaching critical rotation.
The way it's written, it is answered.
No, because in this tidally locked system, you never go to critical rotation. So they're not, like, in a sense, one could say they're not relevant to this question.
And you guys don't agree?
Any last words? Provocative thoughts? Non-provocative thoughts?
I can change.
Yeah, then I think we're gonna end this session, and
Well-
Jared is gonna bring us home with a conclusion, word clouds of what we all think.
Great, thanks. So thanks everyone who filled out the survey before and after the conference, or before and during, really. The question was, in your opinion, what is the biggest current challenge for our understanding of stable mass transfer? And we were trying to figure out a little bit of how to represent this data, and we figured that the easiest kind of population level statements we can make, we just count them, and then we can do various data visualizations. And one is you just count them and make the words bigger. So this is a word cloud. You know, many of us are familiar with the word cloud. And unsurprisingly, mass transfer were the most common things anyone typed. It did very crude data reduction techniques, as you can tell, right? But some of the interesting things is that before we came here, 3D came up a lot. They actually the thing I used wouldn't pick up on the number 3, so I had to clean it and say 3 so that would appear. You know, there were some, sort of like things like 3D observational is still pretty big. You know, angular momentum transport also came up a fair amount, right? There was sort of an emphasis on stability and efficiency, and you know, a lot of these other words that also kind of were put in the question. So then, after the conference, mass transfer was still the biggest. Efficiency was also still, in fact, much, even larger. More people said efficiency was this thing. One thing that I found was really interesting actually was that 3D went down. And I think some of it is because it seems a lot of things that we need to even address first. Bigger uncertainties than just we're at the level where 3D simulations have the most to say, which I thought was really interesting as someone interested also in the 3D simulations. The other thing that was interesting to me was that conservative and non-conservative actually popped up a lot more. People are starting to, I think it's becoming clear also, some of it was whether or not these are equivalent statements of conservative, non-conservative, efficient, inefficient, et cetera. But I think that casting it in that way of how much mass is lost from the system seems to be an interesting thing that's emerging from the aggregate data. One other comment was that I had mentioned to at least some people that we were making a word cloud. And so if I just took the raw data, someone typed beer, 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 beer. So we had terrestrial interference with our signals. And so this is just another a lesson in at least clean your data a little bit.
Or don't tell people what you're doing.
Yeah, or don't tell people how you're going to analyze the data before you take it. That's also probably a good lesson. But of course, these population level answers and ideas only get us so far. So we also wanted to ask you throughout to the room and, sort of do this, pop-up style, but 2 questions. One is, what was your most interesting, I'm going to say both questions first, but question 1 was, what is your most interesting or informative takeaway from this conference? What did you learn? And then question 2 was, how much did your answer change and how for the initial question we posed? What was the biggest challenge? So
Any volunteers?
Any volunteers? We have also asked plants to think about this already.
So I changed my answer quite significantly because I was one of the people saying 1D versus 3D to start with. What I put in the second survey, that I'm a little not worried, but I think we should do better in the way we compare data and observations. Data and models, sorry. There are techniques, Bayesian techniques, inferences that should be used and that not used, and also probably we are at a level that we should not only propagate the uncertainty on the data, but also the uncertainties on the models.
Yeah, that's true. Comparison.
By comparison, yes, I'm the only one, clearly.
No, it's actually very true. Comparison and observables don't appear nearly as much here. Observational does, but
observations even decreases from the start to the S. I have the impression in the word cloud at least that observations have a smaller bit, a smaller share in the second, the post workshop. So
some of it is, scaling.
Yeah, but there is observables, so it's kind of like.
Yeah.
Doesn't per se mean we.
Observables plus observations.
There's also observables in the first. It doesn't matter.
Oh, okay.
Maybe I can jump in because I'm one of those who put it first and then not in the second one, because I think one of the things I learned, and this thing brings it up quite a bit, is that there's much less consensus than I thought on the theory side. So in the beginning, I said we need more observations because I'm an observer. And now I'm more thinking we need to understand the theoretical bit much more. And as I said, I thought there was already more consensus and now I've realized there's things that I thought were more or less established and they're not.
I had completely the opposite kind of thoughts. Now I think, no, we need way more observations.
Always more observations, right?
I agree with you, because I think if you look at the binary models, aren't they like exactly the same as 20 years ago? Like all the parameters are the same parameters as we had 20 years ago. Maybe some parameters now have a bit more of a value, but we need observations to constrain them more.
Yeah, I was one of the people who wrote 3D on the first form, basically a challenge being transferring information from these 3D simulations down to 1D and then standard rapid population synthesis codes. And I'm still kind of on the same page, but now sort of more narrow, trying to think about, like you brought up, like just now, like what part of binary evolution are we confident enough that 3D simulations will help us provide more information than just more uncertainties? And then I think you also asked for a third question about a big takeaway, I think, is eccentric mass transfer seems to be a huge uncertainty, and hopefully in the next few years we can have some improved models on that, because it was really a center of attention on one of the days.
Other volunteers?
I think like when I started, like on Monday, I thought that like I was like you. I thought nothing below 10 solar masses makes sense, but now I think like, there is so much observations in the white dwarf range and blue stragglers range. Like I think like there is a lot of observations that we can do in the like lot of work that we can do in the lower mass range. And another point is I think there is also a lot of mass dependence that we should investigate, like even like things like mass transfer efficiency, eventually it probably will be mass dependent as well. Yeah.
Yeah, I can give my personal thing as well. I think I was one of the people who put efficiency both before and after, but I think I added the word observation in this in the second. So mass transfer efficiency observations, and it is related to some of the things that I was surprised about, how many observational evidences we have that there seems to be fully conservative mass transfer, and then we're just not matching that with MESA. And then with substance, at least I see a lot that, you know, when you determine for the first mass transfer phase, determines completely what your population at the second mass transfer phase is going to be. And so it sets, obviously, all the further interaction. So I think I wrote that mostly because I do think, even though we were talking about that stability criteria, I do think we might be able to make a lot of progress there if we use the data that is apparently already partially out there, but it's just spotted in different samples, different masses, and different observational regimes. But again, I believe in us, or at least a lot of you, or at least you, that I think we can make a lot of progress in that mass transfer efficiency. Yeah.
Just to add something else, I would think before I came here, the biggest thing would be also like the efficiency, the onset of instability and things like that, because I had in my head, like I thought we understood accretion disks and things that to do with accretion disks very well. And I forgot that tides exist. I was brutally reminded that tides do exist and that they do muddle up things quite a bit. So that was a nice reminder.
I mean, for me, I also felt like from Ang's talk that I felt more hope that we can make progress on understanding the role of tides now than I did before before coming to this workshop. That's hope for the future, not our understanding now.
Yeah. Okay. Oh.
I think a broadly similar experience to Amanda. I maybe would have shown up. I actually didn't fill out the survey before coming. Honestly, just kind of wanted to, come and learn what everyone's thinking about. So I didn't have a strong bias in any particular direction, but I probably would have thought, the donor star and its interaction with the Roche lobe is the biggest uncertainty. And I think we had a really fun discussion yesterday about how there are huge uncertainties there, but I definitely am coming away with much more of an appreciation that everything going on the other side of the binary is really just as important. The accretor star, its internal angular momentum transport, its disk, and how its tides might, redistribute. I think just everything to do with angular momentum. And I think I have much more of an appreciation of there are lots of different places that can go. It's not really just in the orbit and some amount of, mass loss through a beta prescription. So it would be worth thinking about, investing in more more angular momentum treatment in general, I think.
Good. Any last thoughts? Mark? Things?
Maybe one more little thing about ties. Yeah, other than like binary systems, we can also like borrow experience or like that people work on exoplanet world, like because one of the exoplanetary system was 12, that system, people just keep observing that system like several times, and that's the only like exoplanetary system have been confirmed with the p dot measurement. And that, yeah, you know, like for exoplanetary, they are not in mass transfer, but like it's like give us like a, because like it give a the time scale for like orbital shrinking. So and also it's not in like mass transfer phase, but it's help us to like very well constrain like how tidal dissipation rate, like just quantify like, yeah, like everything. So like sort of very helpful, help us to understand like maybe tides in general.
Yeah.
I'll just say what I put, because why not? Before this, I just put something random. I assumed that there's before I thought maybe there was a large uncertainty in what happens to the accretor, kind of like what Evan said, and that's what I put. I said what happens to the companion, and after the mass transfer. But after, my whole impression, I'm not a binary person, is that the mass transfer, the efficiency is like the holy grail. And that seems like something that we've just been talking about all week. And that's something that's been kind of like impaled in my mind now. So I'll leave here with that.
Yes.
I had kind of a provocative thought. Do we understand pre-interaction binaries well?
You mean stars?
Single stars?
Depends on how massive they are.
Yeah.
Yeah, well, I think.
And how close you look.
And how close you look, how close you look. Yeah, so how bad it is, how close you look and how massive they are. Yeah, pre the first mass transfer interaction. How well do we understand?
Arguably much better than after.
I do agree with that.
That's fair.
Definitely becomes orders of magnitude more problematic.
Someone who dives into a lot into the uncertainty of the answer to that question in the single star limit, I would say it's still fair to say that after there's a lot more uncertainties. Yeah, because it's all the same uncertainties, and then wildly different core mass ratios and rejuvenation and
The same uncertainties with compound interest.
yeah, and interaction effects, literally and figuratively.